Hello and welcome to this KNX system telegrams and electronics webinar. The electronics will be about twisted pair, and my name, by the way, is Christophe Partoens, so the presenter of the webinar, obviously. So here's the agenda. So first topic will be about octets that I will then compare with the actual serial characters, or I will explain you the difference between both aspects of telegrams, of the telegrams. Then specifically I will talk about the individual fields, the control field, the source address, the destination address. Sorry, this is missing in the agenda, but I will definitely also speak about the destination address. Address type, hop count, then we will end up with the payload, where I specifically will explain the twisted, sorry, not the twisted pair, the TPCI and the APCI, transport layer, control information, and application program control information. And then some specifics on TP, so I will explain you the the concept of collision avoidance that is used for TP, and then a bit on the electronics, so I will show you the choke, how it works, and also the transmitters. I will explain, and then I'll explain you also the principle of SELV, S-E-L-V. As you can see here on the slide, the abbreviation. So okay, let's start with the first topic then. So a telegram in KNX is actually a collection or a series of octets. Here we see them, so I hope this is also clear for you on your screen. So it starts from octet 0, following by octet 1, and so on until maximum 22. Now, there are different fields that can be identified here. So the first octet is actually what we call the control field. The next two octets, so octet 1 and 2, is the source address. So that is actually the originator, let's say, or the individual address of the originator of this telegram, so the device that has sent it, right? And then the next two octets is the destination address. We then need some further information from octet 5 in order to know the address type, the hop count, the length, but I will explain length later on, the actual payload, and then there is also at the very end, the last octet, so to say, is the checksum, which is, by the way, also known, so here indicated as a remark on the slide, this checksum is also known as the so-called horizontal parity check. Okay, I said indeed we need to distinguish octets from serial characters because an octet as such is not enough in order to be successful with this. I mean, in order to bring the message across, we need some additional information, some additional bits actually, in order to send each octet individually properly. And this is this is done by adding 3 additional bits. So as such, these bits have no meaning. I mean, they don't contribute any value to the octet, but they are absolutely necessary in order to transmit them. So what we need first of all is a start bit, which is always 0. And then we will start indeed sending with the lowest. We will start by sending the least significant bit first. Sorry, so bit 0 till bit 7, and then we will add one more parity bit, which is an even parity bit, following with one stop bit, which always has the value 1. So that means in total per octet we need actually 11 bits. So not 8, but actually 11. The even parity bit, by the way, is also known as the vertical parity check. So you might have seen that somewhere in another document. Then, well, then you know you can make the link with this parity bit then. Okay, let's have a look at the first octet of the of a telegram, which is the control field, so octet 0. So the information that we find there is as follows. So here we see the encoding, the individual bits, let's say. The most significant bit is actually about the frame type. The frame type is, well, let's say in our case, it will always be 1, because I will only speak here in this webinar about standard frames, not about extended frames, so only standard frames. In case it would be an extended frame, well, then this first bit is 0. But again, from now on onwards, we will only see telegrams or only consider telegrams where this bit is 1, so standard frames. That means they have a maximum length of 23 octets, so counted from 0 to 22. That's in total indeed 23. Then bit 6 is actually fixed to 0, so all the red values here means they are fixed as such, so they have to be they need to have that exact value, otherwise the entire telegram needs to be considered as invalid. So we also see that for bit 4 that needs to be 1, and bit 0 and bit 1 here also need to be 0. By the way, these bits we call also or also known as preamble bits. They actually announce, so to say, that there will be a new telegram coming. For the rest, there is the repeat bit, so on position 5, so to say, or bit 5, which means that is the bit that indicates whether this is the original telegram or the repeated telegram. In case this bit is 0, it means this is a repeated frame or telegram. And then bit 3 and 2 actually indicate the priority of the telegram, in which we see the values here. So if it's 0, 0, both 0, it means a system. And if it is 1, 1, so both 1, it is actually the low priority. And in between there is urgent and normal. Okay, by the way, I also want to already tell you that the slides, they will be sent to you tomorrow automatically, together with as an attachment of the follow-up email of this webinar. So of course then you can have, then you can check all this information from tomorrow onwards at your own pace, of course. So if I would be a bit too quick now, or if you try to take notes of everything, of course that is not necessary, because you will get the slides anyway. Okay, the next field is the source address. So as I already indicated, this is the actually the individual address of the originator, so the device sending this telegram. Yesterday I had another webinar about topology, and there I explained in detail how such an individual address needs to be encoded. So I will not repeat that here again. If you were here yesterday, then you will have the slides also from yesterday. If you were not here, I just recommend you to maybe follow this webinar also in the future then. So it was the webinar about topology, right? So I will not say any more about this. So this is the individual address of the sender, of the device sending this telegram. Then the next field is actually the destination address. So that would be octet 3 and 4. However, this is not enough information because we need one more bit actually in order to interpret this destination address. So we need also the most significant bit of octet 5. And that's what we see here in the table. So first of all, we see what the value is of the destination address, so of octet 3 and 4. and then we also look at the value of the address type, so the most significant bit of Octet 5. And this will then tell us what kind of destination address we have. So in case of the combination 0, so where all bits of the destination address of Octet 3 and 4, so to say, when all these bits are 0, and the address type, so the most significant bit of Octet 5 is 1, then this is a broadcast message or telegram. In case this is not 0, so the destination address is not 0, then and also the address type has value 1, well then this is actually a multicast telegram, and then the destination address is actually a group address. In case the address type is 0, well then in any case this is an individual address, and then in that case the telegram is actually a unicast telegram. Here we see a bit more details on these different, let's say, different types of telegrams that we can distinguish. So again, we can distinguish 3 types: broadcast, multicast, unicast. So we see again here what combinations are required then. So destination address 0 with address type 1. This is for network management because it's broadcast. Broadcast literally means that it indeed is intended for all devices of the network. So it's actually sent to all. That's indeed by definition what the English word broadcast means, sent to all. And why it is used, I also put here an example. Well, you would use this service or this type of telegram in order to set the individual address of a device that is in programming mode. Multicast, so that would be the combination of address type 1 with a value higher than 0. Well, this is a service, this is a telegram that we will need at runtime. Multicast as such means that I will send this telegram to a group. Yeah? How big this group is undefined. Can also be just one device, can also be all devices of the installation. But it is undefined, so it is sent to a group. And the typical service that is applied there is a group value write. So it will, example given, close or open a relay. Often a binary output example given. In case the address type is 0 in combination with value, then this is a multicast telegram. So it's to a specific individual address. Because unicast indeed means I sent this telegram, or it is intended for exactly one device. So it is sent to one specific device. And a typical service that would be used here or could be used is memory write. So in other words, it is a telegram that we will use in order to commission devices, in order to program devices, or whatever you want to call it. Now, so that is again, these are the types of telegrams that we can distinguish in a KNX installation, so to say: broadcast, multicast, unicast. Some remark on routing versus tunneling. So there's also a lot of confusion about that. Routing is always a connection, less communication, so that means it is either broadcast or multicast. So routing is actually used for network management or for runtime. Whereas tunneling is a connection-oriented communication, which means tunneling is actually unicast and is only used for device management. So I just wanted to add this because I had on several occasions this request or have seen confusion. So I hope that this slide then help you out or can avoid this confusion. Okay, next next field. Well, actually, we already discussed it, but I want to explain it to you in a very specific case. So that means where the destination address is a group address. Then this is the encoding. So according to the project setting according to the project setting for the group address how the group addresses shall be presented, we can distinguish different interpretation, let's say. So whether it's 3 level, 2 level, or 3, it actually defines how we have to look at these at Octet 3 and 4. So in case of a 3 level group address, well, we can say that the main group address is actually our bit 7, 6, 5, 4, and 3 of Octet 3, where the middle group address is actually 2, 1, and 0 of Octet 3, and where sub is actually the entire Octet 4, etc. So as you can see, for 2 level, also their main is like the 3 level presentation, so 7, 6, 5, 3. But sub is also taking then the entire Octet 4 together with 2, 1, and 0 of Octet 3. Okay, so that is what I try to explain here on this slide. By the way, in all cases, it is as there's only one rule that applies here. That is that that group address can never have. It can never be in a situation where all these bits here, so all the bits of Octet 3 and Octet 4 are put to 0, because that would be considered as being an invalid group address. Or in other words, in the 3 level representation, 0/0 is not allowed. Okay, so I am at Octet 5, so I already talked about the most significant bit there, so the address type, so we know that already. So again, in case it's 0, this is used for indicating that it is a unicast telegram. If it's 80, if it has the value 1, then it is actually intended for multicast or broadcast. Next, 3 bits of Octet 5 are the hop count. Hop count I also explained you yesterday. So again, I repeat, if you were not in that webinar, in the topology webinar, you should come back, or or wait for the slides that you have received from yesterday. So that's the hop count. That is for decrementing. That will be decremented by couplers. The next 4 bits, so the bit 3, 2, 1, and 0 of Octet 5 are actually used in order to indicate the extra octets that are in the payload. I'll explain in one of the next coming slides. Because I'm going to look at the payload as such, so the payload, we can say that payload is always Octet 6 plus some extra octets, and the number of octets is actually indicated by the length field, so the LEN field. Again, the length indicated with the 4 last bits of Octet 5. So example given, if Octet 5 would have here in this field, so in the length field, again being the bits 4, 3, 2, 3, 2, 1, and 0. If that would be, if that field would have the value 2, it means that the payload actually exists out of Octet 6, 7, and 8, because of 2 means 2 extra octets besides Octet 6. So again, payload always has minimal Octet 6 plus some extra octets. Okay. Looking at the payload, we can distinguish a transport control field, which is actually the first 2 bits of Octet 6. Right? So it controls, this is the information that controls the transport layer of the KNX communication stack of the device in question. And transport layer is actually what kind of information we find there is how the payload shall be transported. Actually, that is what this 2 bits will indicate. There are 2 criteria in this encoded in this control field. That is the information type. So is the data that is encapsulated in the payload, is that pure data or is it control data? And the other criterion is whether the sequence type, whether this is numbered or unnumbered. So again, information type, so whether this is data packet or control data, indicated with DP or CD, sorry. So it's always bit 6 of Octet 7, and here numbered or unnumbered, N or U, so that's bit 6 of Octet 6. And this will then render the following combinations. So example given, numbered data packet or unnumbered data packet, and so on. Now let's have a closer look again at the control field or at the meaning behind it. So what we see here is the different. So this is an overview of the possible combinations, so to say. So that means in case the combination is 00 or 01, then it is always a data packet. Data packet means okay, starting from bit 1 and 0 of Octet 6, some data will follow. If bit 6 is put to 0, so that means unnumbered, well then bit 5, 4, 3 and 2 of Octet 6 are just meaningless, they have no meaning, so they can be put to 0. If however bit 6 of Octet 6 is 1, then it means okay, this is numbered, and then there will be a sequence number. And as you can already see, the sequence number is 4 bits, so that means we can have a value from 1 till 15, right? If the combination of the bits 7 and 6 is 1, 0, which means unnumbered control data, well then we have to look at the unnumbered means, of course, also here that bit 5, 4, 3 and 2 of Octet 6 are always put to 0, or they are just simply meaningless because it's unnumbered, right? In that case, bit 1 and 0 define what kind of transport layer, let's say, control is involved. So in case of the combination, it is the combination 00, then the telegram is actually a transport layer connect. In case it's 01, it's transport layer disconnect. And then there is the last type, which is the combination 7611. So that means this is numbered control data, and then there will be, because it's numbered, there will be a sequence number, right? What we see here. And also here we have to then look at the bit 1 and 0 of Octet 6. So in case the combination is 10, then this telegram is a transport layer acknowledgement. In case of 11, it's transport layer negative acknowledgement. Here again a summary of what I have just explained, but then maybe how to say, with some additional information in order for you to understand what the meaning is behind all of this. So in case, again, this is the telegram is a data packet, then we see these combinations, so either 0, 0 and 0, 1. And then in that case, bit 1 and 0 of octet 6 are actually the first 2 bits of the APCI. APCI, I'll explain in the next coming slides. In case we have the combination 1, 0 or 1, 1 for 7, 6, well, then this is actually about, then this is control data, and then it's actually, the telegram is about controlling indeed the transport layer. How to control the transport layer? Well, there are 4 services defined: transport layer connect, transport layer disconnect, transport layer acknowledgement, and transport layer negative acknowledgement. And that is what I have explained here. So indeed, control data, either one of those 4 services. Now, for you to better understand why why we need this, or what is the meaning behind what the purpose is of a control data telegram, well, here in plain English, actually, whenever the service encapsulates a transport layer connect, the telegram actually says hello, so that to the receiver or the destination, of course, hello, I want to talk to you, right? That is actually what's going on here. It tries to set up a conversation. Yeah? So it's typically something that you will need for commissioning a device, because more telegrams will follow. So there is indeed a kind of session going on. Kind of session, a communication session will be created and will go on. So that would be the first message, to build up that connection, to build up that session. So nearly literally saying, hello, I want to talk to you. When it's finished, then ETS, because it comes from ETS, will say, okay, for me this conversation is over, goodbye. So then the device knows, okay, I don't expect any more messages in this specific session. And during the session, there will be messages exchanged, and in order to confirm such a message, there will be a transport layer acknowledgement used in order to indeed confirm that. So that's literally, okay, roger that, or if it's not good, sorry, I didn't get that. In that case, a transport layer negative acknowledgement will be sent. So that is a bit the meaning of control data. That's why we need it. Again, this is typically used for programming devices. In case of a data packet, well, then actually these data packets or the telegram is actually a command. It literally means do this, right? If this is indeed such a telegram, well, then the telegram will always contain a command identifier, which is actually the APCI. It controls indeed the application, right? Not only it is clear which command it is, which is in the telegram, but also the data belonging to that command, of course. And that brings me then to the APCI, of course, because the APCI is then so in case it is the telegram is a command and not control data, well then we need to look further in the payload, and then we can distinguish indeed different APCI lengths. They have either length 4 bits or 10 bits, right? As such, if indeed the length is 4 bits and the data length, so the data that comes with the command has a length lower than 6, well, then the data can still be fit into octet 6. So that's typically what we see for a group value write example given, where the length is indeed smaller than than 7 bits. So typically binary output example given, so on off, or dimming 4 bits. So then typically you put also the data. So the telegram says actually, okay, change this this relay. So change the status of the relay, and with the data you say, okay, what shall I do? Close it or open it. So that would be a typical example here. Okay. Then this is all I wanted to say about the telegrams actually. So ending of course with the checksum, but that I explained in the beginning. So okay, then twisted pair, the physical details. So I'm actually going towards the electronics now of twisted pair. And here we can see what has been defined as being a signal having shape 1 and a signal having the signal shape 1 and the signal shape 0. Sorry. So first of all, there is a constant DC level which shall be minimal 21 volt and maximum 32 volt. Otherwise, this is not considered being a 1. Right? If we, however, want to send out a 0 on twisted pair, then the signal shall have this shape. So the shape 0 looks like this. That means there shall be a voltage drop of minimal 3 to 10 volts. So and that is of course a reference to the DC level. So there shall be a drop of at least 3 volt. So this shall be at least minus 3 volt or minus 10 volt maximum. The time of the voltage drop shall be 35 microseconds, and then there will be an overshoot like this, and this overshoot shall have a maximum of 13 volt, also again referred as a reference or how to say, as a reference there. The DC level is of course also used. So not more than 13 volt should be the value of the overshoot. And for best practice, the recommended cable our recommended cable, in order to guarantee these shapes here, are the following cables here. So in case that would be in your interest, I just added it to the slide. I often get that question, so therefore I added it. Then for the physical layer still, so sending telegrams, I want to point out that the following situation is there. So if we list the octets of a telegram from 0 to 22, so from left to right, then please note that they are indeed sent as such. So they will be sent from left to 0, or from octet 0 till octet 22 maximum. However, within an octet, the bits are sent in the opposite direction. That means the lowest significant bit will be sent first. So that's then from right to left. That is important for you to know, because it is important for what's coming next, collision avoidance, in order to explain you the principle behind that. And also I want to repeat that a signal with shape 1 is considered as a passive signal. It's just always there and exactly like that. unless this happens, so unless there is some activity, so therefore we say indeed that signal with the shape 0 is actually indeed an active signal. And this brings me then to the collision avoidance. So that is what we see here in this slide. So suppose that two devices are communicating with one another, or that two devices are sending at the same time. Maybe that's actually the better way to express it. So we need to consider indeed two devices. So device A and device B both have a transmit side and a receive side. So TX, RX. So both of them have that, of course. So in case that device A and B are sending at the same time, then we have actually this situation. That means virtually the TX, or the sending side of device A, is actually, again, virtually connected to the receive side of device B, and vice versa. Again, this is a virtual situation. This is not what physically will happen, but it looks like that. Just a brief moment, please. Okay, so what then happens is the following. If so, we need to consider the different cases. So, in case device A receives from B the same signal as B receives from A. So, example given, they both. So let's say device A sends here a 0, and device B also sends a 0, or both. In both cases it's 1, so device A sends a 1 here, but B also sends a 1 here. Well, in that case, both devices will continue sending. If A receives from B a passive signal, so that's here. So here comes a passive signal. So in other words, here comes a 1. And B receives from A an active signal. So here comes 0. Then A will continue sending. So device A will then in that case continue sending, and B will stop. The other way around, if A receives from B an active signal, so here comes a 0, and B receives from A a passive signal, so here in this case comes a 1, well then it's the other way around. Then device B will continue to send and device A will stop. So this is how collision detection, avoidance, actually works for the physical layer, for twisted pair. So that means in the following situation, so suppose that we had this situation where one device sends a group value right to 3 other devices, to 3 receivers. Then these are the possible reactions: acknowledgement, negative acknowledgement, or busy. Now, just as an exercise to see which one of these signals will have, so if they, of course, send at the same time their reaction, so at the same time comes on the bus an acknowledgement, a negative acknowledgement, or a busy signal, then we can indeed understand now who will be the winner here. And that's what I try to do here in this exercise. So just to compare, so I repeat again the principle. So it is always sent from lowest significant bit to the most significant bit. 0 wins because it's the active signal. In case of the same value, the device will continue. Both devices will continue sending. So if example given, there would be a collision, or if I would have at the same time a device sending an acknowledgement and negative acknowledgement, then this is the situation, right? So we will see that indeed eventually the detection or the avoidance will be done right on bit 6 in this case, because it starts from the lowest significant bit, so here, and here we see indeed 0, 0, so that's equal. There's no decision who has to stop yet. On bit 1, there is no decision either because it continues, so it will also continue here. Both 1, so it continues, both 0, both 0. But here, indeed, at bit 6, we see the first time a difference. That means that in this case, indeed, the device sending the negative acknowledgement will continue sending. So the device sending the acknowledgement will stop sending. That means, and this is indeed logical, because it is important that the negative acknowledgement wins over the acknowledgement. The sender of the telegram needs to know whether there was at least one device that didn't receive it properly. So therefore, in that case, indeed, the negative acknowledgement is the winner. In case of busy, we can see that it starts also here from, of course, from the lowest significant bit to the most significant bit, so 0, 0, 0, 0, and then the decision will already be made on bit number 2, because we can see here already a difference in the signal or in the telegram. That means also here the device with the busy signal, with the busy reaction, will win over the positive acknowledgement. Okay, twisted pair line, the minimal setup and extensions. Next topic. So in order to set up a twisted pair line, a KNX twisted pair line, it always starts from a choke, which needs to be powered by a power supply unit, like this. And this will then indeed, from that moment onwards, we have indeed a twisted pair line or a twisted pair line segment to which we can add devices, like this. If we want to extend this line, then we can do this as follows. We need to use, first of all, a repeater, and then we have indeed we have added another segment. However, this is not good enough because it also needs to be foreseen from a choke and a power supply. And from that moment onwards, we can then add devices to this line. Another way to extend it is by means of a coupler. So we then go higher in the topology. Again, topology was another webinar. So I explained couplers there. So I will not repeat it here. So we can then also add a coupler. This will indeed allow us to do this. So there will be another segment added, which is, however, higher in the topology. But this also needs a choke and a power supply, and from that moment onwards we can also again indeed add devices. So this is how twisted pair lines can be set up and extended. The twisted pair line segment limitation is 64 devices. Actually, this is coming from the 90s, so when indeed KNX was born, so to say. Then the technology back then, back then the limitation was indeed 64 devices. However, today these devices and the chokes have been updated, so they have improved technology, and actually this that means that the actual limitation now depends on the manufacturer. So it's not longer 64 devices. However, the 64 rule is still applied. So it's still considered as best practice. And also one more remark that I want to make. As such, it is not important where the actual power comes from. Yeah, the power can, that means one power supply unit could indeed serve for different lines or line segments. That is actually as such not important. Therefore, we also see different PSU variants. So going from 160 milliampere to even 1280 milliampere, and all these values in between. Here we see the electronics of a choke. So this uses a transformer. And the transformer actually as such, and that is actually the most important conclusion, it actually has as a consequence, or the advantage is that we have indeed a galvanic separation actually between, well, it actually gives a galvanic separation, which then has as a consequence that it is, the consequence of that is that the bus is indeed completely, so the twisted pair bus is completely self. This is for the power supply. What we also need on the other hand are the device transmitters, so that it looks like this is actually a similar technology. Also uses a transformer. So also we can again see here complete separation, galvanic separation. That's why when there is a bus reset, devices, twisted pair devices are not affected by that. So that's the reason why actually. What we also can see here is indeed that whenever a device wants to transmit something, here this switch is closed, or these two switches are closed, which means that indeed this will cause a voltage drop. So therefore 0 is indeed considered being an active signal. Also here there is a transformer on board, and as I said, all this leads to self actually, so the safety extra low voltage, which means that there is indeed an extra low voltage. There is low risk of accidental contact with higher voltage because of the galvanic separation, and also important, there is no return path through earth. That means also, so this avoids indeed electric current that would go via the human body. Okay, this was the last slide of the webinar. So I have done talking, except for one thing maybe. I still want to point out where you could find that other webinar that I've been mentioning now a couple of times already. So simply, if we start from knx.org website, you can then find these webinars under, yeah, webinars. And here you see the list. So they are listed here, and see if the very one I'm talking about is here. Yes. So next week somewhere, or within 2 weeks, there is indeed network topology and couplers. And also, example given this afternoon is also could be interesting for you, so to understand more about the communication stack, etc., etc. Just to point out, we have several topics, and they are actually quite easy to find. Also, in case you would like to have a recording or would like to watch it again, well then you should click here. So on the on this very link here. This will then bring you to, well, I can actually click on it, of course, to a YouTube playlist where you can find all recordings. However, one remark I need to make here in this very case is that for this very webinar there's no recording yet. Why? Well, this because it was the first time I presented it. So I'm recording it right now. The recording will be processed and will also be published there in the next coming days or next coming week. And before I conclude the webinar, I want to still present a few extra slides. And while doing that, I want to thank you for being here. I want to thank you for your attention, for considering KNX. And maybe we see one another in one of my future webinars. So thanks again and goodbye.